Our next speaker is AU Nachiketh Kumar, and he'll be speaking about assessment of thermochemistry modeling for hypersonic non-equilibrium flow and Martian atmosphere using SU2-NEMO. So we have some of the SU2-NEMO folks here in the room, so I'm hoping for some good discussion. I'm sure they're interested to see what you've been up to. So whenever you're ready, take it away.
Yes, sir. Thank you, sir. Thank you for the introduction. So hello, everyone. My name is Nachiketh Kumar. I am an undergraduate student currently pursuing aerospace engineering from MS Ramaiah University of Applied Sciences, Bangalore. Today, I would like to talk about my research work on assessment of thermochemistry modeling for hypersonic non-equilibrium flow in Martian atmosphere using SU2-NEMO and Mutation++. This research work was carried out under the guidance of Dr. Gopal Krishna Narayanan, who is the alumni faculty from Department of Aerospace Engineering. We have been using SU2 for past 1 year, where we have simulated various hypersonic test cases. So in this research, mainly this work mainly involves the prediction of accurate aerothermal condition for spacecraft entering Martian atmosphere. So in this presentation, I'll give a brief introduction on the non-equilibrium flows, motivation and aims and objectives of the current work, followed by geometric and free stream condition and solver implementation. I'll talk about key results that have been obtained using SU2-NEMO solver, finally ending up the presentation with the concluding remarks. Just a second.
Yeah, there may be a little lag, so you have to be a little careful.
Yeah. Yeah. So non-equilibrium flows are the situation in fluid dynamics where flow will no longer behave according to the ideal gas principles. So these kind of flows will usually experience high vibrational excitation, dissociation, and recombination of gas molecules. And even at extreme temperature, even ionization is also absorbed. All these phenomena are basically termed as real gas effects. So this actually happens due to the transfer of high kinetic energy from the free stream, which gets converted to internal energy of the gas across the shock wave, creating a high temperature in that region. These are predominantly found in re-entry vehicles and high enthalpy hypersonic flows as well. So the figure above describes the typical flow features of the blunt re-entry vehicle, and the picture on the right shows the non-equilibrium region behind the shock wave, where you have a vibration excitation region and relaxation region where gas molecules tends to attain equilibrium state. So at this condition, where we observe complex vibrational and chemical kinetics at the local region of vehicle surface, one of the hardest part is to accurately predict the surface parameters, specifically to compute the heat flux data across the surface of the body, since it plays a very important role in the design characteristics, designing of Martian hypervelocity vehicle. And on top of that, given that the low characteristic vibration temperature of CO2 molecule is expected to play a significant role in non-equilibrium flow features, so the main focus of the main aim and objectives of the current work will be to model the aerodynamic environment and to study the non-equilibrium effect on the heat flux in CO2 dominated flows, to carry out the validation of SU2-NEMO modeling capabilities for high enthalpy reacting flows with the experimental data, and to assess the fluctuation of heat flux due to different thermochemical modeling assumptions, and finally to compare the results from SU2-NEMO and the fluent solve. For this current study, we have taken two different geometries, the geometries of large angle blunt cone body, one having 120 degree apex angle, another with the 60 degree apex angle blunt cone. So these geometries are basically used as a 4-body configuration for hypersonic re-entry vehicles. The 120 apex angle has a base radius of 50 mm and nose radius of 25 mm. The 60 degree apex angle have a base radius of 40 mm and nose radius of 35 mm. These are the free stream conditions that have been taken from the experimental paper, which was carried out by Professor Mohammad Ibrahim now who is working in IIT Kanpur. So basically, he carried out experiment in high enthalpy and low enthalpy flows using FPST, which is a free piston shock tunnel in ISC. So basically, in this case, I have taken a high enthalpy case where the enthalpy is 3.6 megajoule with a Mach number of 5.87, pressure having 572 Pascal with the temperature 739.85. So the test gas used here is pure CO2 gases, and the table above shows the properties, the gas properties that was present in nozzle supply region. These were the total pressures that was present in the nozzle supply region. This here we have the species mole fraction of different CO2 species that was predicted in the nozzle supply region using Chemkin software in the experimental data. All the reactions that have been described here was taken out from the experimental paper, which was calculated by Chemkin software in the experiment. So here is the whole implementation and workflow, how the whole solver works. The coupled system of SU2-NEMO and Mutation plus plus, which is a thermochemical library, helps in computation of thermochemical properties and transport properties of the gas mixture. Since we have a different chemical mixture and we have a different reactions occurring, we have created a mixture file and reactions file where we in the mixture file, we'll add composition and species that are present in the free stream condition, and the reaction file will be having all the reactions that are taking place between the molecules that are present. So this is the computational mesh that have been used for simulation. The left one shows for the computational mesh for 120-degree Berlin cone, and the right is for 60-degree Berlin cone. All the computational mesh has a similar boundary condition where we have far field, wall, outlet, and axisymmetric axis. A structured mesh was created using a commercial mesh creation software with the grid size of 0.5 million. And even boundary layer inflation layer was added to the wall regions to capture accurate surface data. The first layer spacing was 1 into e to the power minus 6. Since we didn't have a good computational facility, we had to stick up with 0.65 million grid cells. And since we have also not done the grid independent study because there is no availability of HPC systems as far as of now, but it is under our future scope. These are the boundary conditions that have been implemented for the above domain. These are the solution methodology that have been implemented in configuration file. The fluid model is mutation plus plus, as we are using thermochemical library here. And this gas model is the name of the mixture file that have been added to the database of the mutation plus plus. And the gas composition, we usually add the mass fraction of the gas species that have been that are present in the free stream condition. Talking about the results, so initially we have simulated, we carried out a validation part for the gaseous species that was present in our nozzle supply region. So the experimental data and the a solution that was found using mutation plus plus agreed matched pretty well at the corresponding temperature that was present in the nozzle supply region. So basically, this mole fractions that we obtained is mole fractions of the gas that was present in the nozzle supply region, as I mentioned before in the previous table. And the graph in the right describes about the diffusion flux variation. Basically, it tells about the rate of reaction in which direction is it moving in the temperature gradient, or is it moving against the temperature gradient. These are the results that we have obtained using SU2-NEMO for 120-degree blunt cone. Quantitatively, the quantitative result for all the three thermochemical assumption was found to be almost similar, except at the case of stagnation region where shock standoff distance was predicted higher in the case of equilibrium compared to non-equilibrium, both the non-equilibrium cases. And from the table, you can come to know that non-equilibrium for reaction and the frozen state both was matching perfectly with 2.22. And for the equilibrium, we used to get 4 mm as a shock standoff distance. And since we didn't have experimental pressure value for throughout the surface, validation was only carried out in the stagnation region, where stagnation region in the experimental and the stagnation region that was obtained using the SU2-NEMO at frozen chemistry, and both the reaction mechanism matched pretty well with the experimental data. Here in along the Y position, you'll find a drastic decrease in the pressure due to the flow going near the expansion in the curve region near the nose part. The reason why you have obtained a drastic dip here is because of the expansion over expansion, and due to the recompression of the higher angle present in the conical region. So these are the temperature contours that we have obtained. It's evident from the contours that the higher temperature was predicted for higher, both the translational temperature and vibration temperature was predicted higher in case of non-equilibrium compared to other two assumptions. And talking about heat flux variation, for the reaction mechanism assumption, we got a pretty good results near the stagnation region and near the aft region, where pretty much the heat flux data matched with the. But in the case of equilibrium assumption, it's obvious that we have got higher over predicted heat flux data, which was found to have an error of 50% from the experimental results. And yeah, just a second. Once again, in the Mach contour for 60-degree blunt cone, similar as I said earlier, which was also seen in the case of 120-degree angle blunt cone. Here, the flow feature was found to be similar for all of the cases, except at the stagnation region, where the shock standoff distance was predicted higher in the case of non-equilibrium again. Talking about the pressure variation across the along the surface region, we have a drastic decrease in the pressure, and almost for every models the pressure didn't vary significantly. Almost all the models showed similar results with no significant changes along the surface. And the experimental result at the stagnation region matched pretty well with the reaction mechanism and frozen chemistry model. Since we have a pretty lower angle in the conical region, we have not found out a dip region that we have found out in 120-degree case. So these are the same temperature contour, the vibration and temperature contour, and translation rotation temperature contour for a 60-degree blunt cone. Again, in the 60-degree blunt cone, we had the much deflection was found in the heat transfer near the stagnation region, but has in the half region the numerical results and the experimental data pretty matched. It's not accurately matched, but it's closer to the experimental data, and has obviously in the equilibrium higher error was found out along the surface, along the body surface. So these are the stagnation line properties for 120 degree blend cone. The plots in the left represent the mass fraction variation along the stagnation line across the shock wave in front of the blend cone body. From this plots, it is evident that the mass fraction are changing across the shock, where the shock is sitting exactly at 2 mm region, which further tells us a recombination and dissociation process have been taken place in the fluid flow simulation. Here in this plot, actually, we have plotted a translation rotational temperature and translation vibrational temperature profile along this stagnation line. So at 2.5 mm from the surface body, we have a shock region. So in that shock region, you expect a drastic increase in translation temperature, causing a thermal non-equilibrium state in this region. And due to the property of CO2 gas, where it has the lowest relaxation time, it tends to reach the equilibrium state really quick in this region, and eventually both translation temperature and vibrational temperature are becoming equal in the equilibrium attainment region. And this contour represents the degree of thermal non-equilibrium, which is basically obtained by subtracting translation temperature minus with vibration temperature. So no much region of thermochemical non-equilibrium regions are found near the strong shock, because strong shock has a higher residence. The post shock of the strong shock, post shock of a higher strong shock has a velocity. What I mean to say is the residence time of the flow behind the strong shock is very much lower than the relaxation time. This might be the reason why we are attaining a higher, like a really quick equilibrium state. And as we flow across the shock wave becomes weaker, where you can find a significant amount of thermal non-equilibrium happening here.
So just about 1 more minute, if you can wrap it up. We're running out of time.
Yeah,
Sorry.
yeah.
Sorry.
So similarly, for 60-degree angle of attack, we have found the fluctuation in mass fraction along the stagnation region. And in this 60-degree region, due to the rapid expansion of the flow field near the blunt cone nose area, we have found out a property. It's actually called as population inversion in vibrational mode. This happens due to the rapid expansion, the translational temperature drastically decreases in this region. So this was mainly found out in the case of 60-degree angle of attack, but it was not found out in the case of 120 degree blunt cones, due to the presence of strongest shock presence all over the body. So in the final, we have carried out a code-to-code comparison with the fluent data. Fluent data eventually under predicted the surface pressure as well. But in the case of 60 degree, all the pressure data for every different chemical model give a similar results, except at the strongest region near the stagnation region. So these are the heat flux comparison, which was compared with the Fluent. Fluent also provided almost constant heat flux near the nose region, and even the stagnation region for the 60-degree blunt cone was also over predicted in this case. So with that, from the data that we have obtained using the simulation, we can conclude that heat flux analysis demonstrate a significant difference for equilibrium and non-equilibrium flows in thermochemistry assumption. Heat flux and the pressure was, especially for equilibrium model, heat flux and pressure was over predicted in the most of the cases, and reaction mechanism and frozen model showed no significant change while predicting the pressure, but exhibited some differences in predicting the heat flux. And in the thermochemical model, higher shock standoff distance was predicted than non-equilibrium flows, and code-to-code comparison with the fluent showed that SU2-NEMO have better capability in predicting the heat flux at non-equilibrium conditions. And the state of population inversion, as I said earlier, in the apex angle of 60 degree, it was found near the conical region. So as a future scope of the current project, we are trying to implement catalytic wall. So since in the real world, we don't have a perfect isothermal wall condition, so we are trying to implement catalytic wall. And since we don't have high HPC systems currently, we look forward to perform 3D simulations as well, and to compute radiative heat flux at higher temperature. So these are the key reference paper that have been referring for the current project. Yeah, thank you so much.
Okay, thank you. So we're a little tight on time, but we can maybe take one question while we do the transition. If anybody in the audience here has a question, Marco, see your hand.
One is to do comparison of the influxes of the wall, for which I suggest to do a grid independent study with respect to the height, with respect to
yeah.
These are that has a significant influence on the
Could you hear that first suggestion from Marco to do a grid independent study near the wall?
Like I didn't get the question, sir. Actually, I couldn't hear the question.
Comment. He was suggesting that you perform a grid refinement study, especially near the wall, for some of those comparisons you were showing with heat flux. It was the heat flux.
Yeah.
Yeah, just to make sure your grid converged. So you've got to find enough mesh there that you're, the solution is no longer changing for the heat flux. I think that was part one. There's a part two. Okay, yeah, and then his part two was that the catalytic wall boundary condition is also already implemented in SU2-NEMO. So you might want to give that a look before you guys spend too much effort. See if
yes, sir. Yes, sir. Yes, sir. Yeah, it is actually planned for our future work, implementing the catalytic boundary condition.
Okay. All right. Well, thanks again. We're gonna